this guy Felix is a perfect example of what we're going to talk about today, which is gravitational potential energy. Okay? It's the energy associated with the fact that I'm at a very, very high elevation. Right? He has this potential to fall, which he does. And what does that potential energy turn into as he goes? Kinetic energy. So some of you have heard or read a little bit already. Before I talk about the science, just an announcement that the evaluations are come up. This explains my tie. And here's why. 4 years ago, I got this comment. Let me fix this, make it even nicer. Perfect. Here's the comment I got. First of all, this person said, oh, it was a good class, great professor, but physics is really cool anyway, so no problem. Then he or she went on to say he always wore those dirty old Vans. As a professor, I think he should have dressed more professionally with maybe a pair of dress shoes, but other than that, etc., etc. Okay? So in light of this comment, the last week of class I always wear a tie. So I come with complete professionalism so as not to offend anyone who might be offended by my dirty old Vans, which they weren't even Vans, they were actually dirty old Airwalks. Oh, I don't know if anybody even has those, but those are now long gone. Okay, moving on. You'll see that. I'll send an announcement about it on the island page, but I think you're all familiar with it. It's not too hard. This is the less fun part. The final exam's coming. It's going to be very familiar. You've had basically drills, right? Exam 1, exam 2, they gave you a lot of understanding of how the exam is structured. It's all the same rules. Don't miss the exam. A few years ago, I had 3 students miss the final exam. They showed up at the end of the final exam. I didn't care. We just took it. They were really freaking out, okay? So for your own sake of stress relief, just show up on time. When you show up 3 hours late and you realize you're 3 hours late, you start to lose your mind. And the 3 of them did, but they took the exam and did fine. It's in here, Physics 2000, next Tuesday, June 11th, it's 3 p.m., it's 3 hours. You have basically a 3-hour time period. Yeah? I don't know yet, I haven't made it. But I did post, as of right now, I posted a practice final, which it will probably look very similar in a sense to that. Maybe fewer, maybe more, I don't know. But look at the one that's on iLearn. It was posted just as we started this lecture. It's up. I'll talk more about that on Wednesday, but now you have already some study guides in hand. There will be an announcement about other ways to study as you go, review sessions, etc. Again, just to emphasize, I started getting really fancy with my PowerPoints this last week. Don't forget to come to the exam. It's the best thing you can do to succeed in this course, is show up at the final exam. Okay? So let's move on. This is where all the fun begins. As far as physics goes, energy is where all the fun in physics is. Okay? So we're going to talk about conservation of mechanical energy. Mechanical energy, as you'll see, is basically kinetic and potential energy, which some of you have heard about. And then we're going to distinguish some different types of potential energy. One is gravitational, which is the one we'll talk a lot about, and we'll briefly introduce or wait till the next time to talk about elastic potential energies, which is, again, you know this, we talked about it with springs. When I squeeze a spring, the spring wants to push back. And so I've stored energy in that spring, and it wants to basically release it. So let's look at the basic energy model. I think most of you have an intuition for this. Some of you have a misintuition because of weird New Agey stuff. Like, dude, man, I got some serious energy from that experience or whatever, right? It's not that, okay? This is physics. That's something else, sometimes called metaphysics. But let's talk about the basic energy model. This is how we think of energy in science. And this is across fields. The energy of a system is a sum of the kinetic energy, the potential energy, and the thing called thermal energy. Okay? We're going to break down all of these different pieces. Thermal energy is the subject of the next course. And so we'll only introduce it this week, and you'll see some examples, but we won't study it too rigorously. And the basic idea is that the change in a system's energy, so the change in the total energy in the system, is basically broken up into these 3 pieces. It's the change in kinetic energy, the change in potential energy, and the change in thermal energy. If I take an ice cube and I put it out in a warm room, thermal energy is being added to that ice cube, causing it to melt. Right? That was a change in thermal energy. The other way you can think about that is that those molecules of H2O are given kinetic energy, right? They start to move more. We're going to show that kinetic energy is the energy affiliated with movement, right? And then the potential energy is the energy that was essentially stored in that ice cube before all of these crazy things started happening, okay? And we're going to define these very, very carefully, but we're doing mechanics. So we won't talk too much about ice cubes. That'll be the next course. We're going to talk about moving objects, classical moving objects. And here's the way to think about it. Energy can basically be transferred to or from any given system. So I look at a system and I say, this is the system I care about. And the way it transfers that energy is by doing work. Let me give you an example. Here's a bowling ball on a rope, a cable. Okay? It has affiliated some energy, some potential energy there. Is there kinetic energy? Not much. It's not moving. Right? There's thermal energy. It's warm. Now I have to do work. Watch what's going to happen. I'm going to do work on this bowling ball by pushing it with a force over some distance. What have I just done to the bowling ball? I've given it energy, right? So from the perspective of this bowling ball, it has now gained energy. What's it going to do when I let it go? It's going to convert that energy into what? Movement, right? It's going to turn into kinetic energy. Okay, so now you get the point. Bowling balls are a good example. We'll come back to that one in a little bit. But what had to happen for that system to gain energy was that I had to do work. Do you remember this example when we were talking about angular momentum? I had to apply a torque to Andrew's arm to make him spin. That was energy being done. I was applying a force over some distance. I was adding work to the system, and the energy of the system changed. Okay? That energy was angular momentum. It was the movement of him spinning around. Now, one really cool thing, we just saw this a second ago, is that the energy can be transformed within that system between kinetic energy, potential energy, or thermal energy. When I held that ball up here, before I let it go, it was all potential energy. When I let it go, it converted it into kinetic energy. So it was transformed inside this object, it was transformed. And these processes don't change the total energy of the system. In an ideal system, we would say that the change in energy of that system was zero. It went from one type of potential energy to another type, kinetic. The total energy was the same, or it was conserved. And we'll see more examples of that. So here are the two we'll deal with mostly here. We're not going to talk too much about thermal energy. We're going to talk about kinetic energy, which is an energy affiliated with movement and mass. And then there's gravitational potential energy, which is associated with position inside the gravitational field. Okay? So here's how we write them down. And again, some of you have seen this. The kinetic energy is 1/2 mv squared. It has to, if I have a massive object that is moving with speed v, I have kinetic energy. Okay? What happens if I have a massive object that is not moving in my reference frame? I would say that it has no kinetic energy. Right? So if either of these are 0, mass, or v, I can't have kinetic energy, at least in classical physics. Now, the other one is the one that we're going to deal with today. We're going to really work to understand this. The other one is called gravitational potential energy. And again, you have an intuition for this one. If I take this bowling ball and I put it down way, way at the bottom where it's resting, I would say that it has some potential energy. What does that bowling ball want to do? If I cut the cable, where would it go? To the floor. It would go down. It would go with a speed, some speed, it would free fall to the floor. Right? So it has affiliated with it the fact that it's elevated off the floor about a foot or so. It has gravitational potential energy. It has a mass. It has a height above 0 that gives it potential energy. Now watch. Why does lifting weights work? This is a good question I should ask. If I lift this bowling ball up, I'm doing work on the object. What have I just changed? Its position. Not its kinetic energy. It's still not moving. But I've now lifted it higher away from the center of mass of the planet. Right? The gravitational field, I pulled it further. Which way does it want to go? Down. What do we know from kinematics? Will it go faster if I started from here to the floor, or if I started from here to the floor? Which one will give the greater speed when it hits the floor? Higher up. Okay. So we have an intuition for this. Now we have equations that tell us this precisely. Okay? If I have gravitational potential energy, if I lift an object up, I can restore more kinetic energy later when I let it go. Who's ever seen these energy storage containers where they basically just pump water up into a big tank? You've seen them basically for your plumbing, right? They put water in a tank so that you have water pressure in the tank. Do you see that the water pressure, the reason the pressure comes out of your faucet is basically the kinetic energy of that fluid, and the reason they elevate it up into a water tower is to build its potential energy. So in communities where you have, like if you're in Joshua Tree, town of Joshua Tree, every little neighborhood has its own little water tank. And what they do is they elevate it a certain height to give it potential energy in the gravitational field so that when I turn on my faucet, it comes out at a certain velocity. Yeah? And we'll talk about that. The whole class will talk about that. So here's the easy part. One last point here before I move on. Is that unlike all those vectors that we had to deal with, energy is a completely scalar quantity. There's no x and y and z components of energy. It's just a quantity that we've added to the system. This makes the mathematics usually a lot easier when you're analyzing these problems because you don't have to worry about how things are moving in a vector field. Okay? And just to be careful, here are the energy units. So if I look at 1/2 mv squared, we know mass is kilograms, velocity is meters per second, that quantity is squared, and so the units are kilogram meters squared per second squared. Right? These are just dimensions. And this thing we call a joule. Right? So when we look at, and we'll see this in the homework, when you read the back of a cereal box, it tells you how many calories are in a serving, right? That's a really confusing number because the nutrition industry has screwed it all up, okay? Those calories that the nutrition industry uses are actually called kilocalories, okay? In physics land, we call that a kilocalorie. So when I eat one of these little Rice Krispie treats that advertises that it's 100 calories only, so it's about like a quarter inch on the side. When you eat that 100 calories, you're actually basically eating 100 kilocalories worth of energy. And when you convert that into joules, it's a very small amount, which you'll do in the homework and see that conversion. Okay? So think about what that food is. It's basically stored potential energy. When I'm hiking at Mount Whitney, I eat a lot of M&Ms because I eat the stored energy in those M&Ms, and it turns into the kinetic energy of my legs moving through some chemical transitions. Okay? So note that the gravitational potential energy is mgy. So again, mass is kilograms, g is meters per second squared. It's an acceleration in another distance. It comes out to the same units. So at least it checks out that both have the same dimensions. And here's a really simple example, right? If I take a 1 pound object moving at about 10 miles per hour, this is something like a heavy ball, right? This thing has a kinetic energy of about 4 joules. Just to give you a ballpark figure, the joule is basically this unit that's kind of things that we think about a lot. Kind of kilogram masses moving at miles per hour, a few miles per hour scales. That gives you about a joule. Let's see if you understand the littlest, simplest bit. Take this first one. You should all have access to it. I gave you the number, I think. Here's the question. A child is on a playground swinging motionless at the highest point of his arm. Okay, so just like this bowling ball. Motionless at the highest point. Okay. Which energy transformation takes place as he swings back down through the lowest point of the motion? Okay, so just take about 30 seconds. See if you can either do it from what we just talked about or if you have some prior knowledge. Here's your intuition. When I'm sitting, you know that part in the swing where you get right up to the front and you feel a little bit weightless? That's the best part. I'm stopped, and then I move. And this is asking about that transition. What do I do? Okay, so take about 10 more seconds. Okay, 3, 2, 1. Get those last few in. Okay, I'm going to call this perfect. 89% of you said B, that you go from stored potential energy. I don't know where the other 11% of you are, but you went from stored potential energy, you turned it into the energy of movement. or kinetic energy. Okay? Let's try a different one. This one's a little bit harder. But not that much. I mean, come on. Come on. It's energy. It's easy to think about. Take a minute. Here's the idea. Rank in order from the largest to the smallest the gravitational potential energies of these different balls being thrown around. There's one that's labeled at the very top. It says that the velocity is equal to 0 there. Right? So that one's an easy reference. I throw the ball up, it stops, it starts to come back down. These vectors show its vector velocity. So just rank them in order. Which one has the largest to smallest gravitational potential? So let me pause for 1 second. Wait, let me pause. Oops. So go ahead and try to answer. Did anybody work? It doesn't have any responses yet. Okay. Go ahead and answer, and then we'll pause for a second. Okay, wait, let me pause it here. Let me go back 2 slides really quickly. Here. How do we define gravitational potential energy mathematically? Gravitational potential energy is its mass times some number times its height. Okay? All this thing cares about really is how high it is from the point of reference, the ground in this case. So when I go to this question, are any of these the same? Are any of them at equal height? 2 and 4. Okay? So that immediately cancels out some of your answers. Take another few seconds and see if you can get which one it is of the last 2. So we know that 2 is equal to 4. All we care about is how high up it is. Take 5 more seconds. I think most of the people have responded. Okay. I'm going to round it up. So this time, this is even better. 91% said D, that 3 has the greatest gravitational potential energy. It has the greatest height, right? If I do this with a bowling ball, is this higher potential energy, or is this higher potential energy? The second, right? All that it matters, it doesn't matter about the path that it traveled, which we'll see. All that matters is how high it is from the ground or from my reference point. Okay? So in this case, 3 has the highest, it has the largest value of y in this case. 1 is the lowest. 2 and 4, even though they have this different directions, they're moving in different directions. All we care about today is potential energy. So let's talk, somebody asked, can there be negative energy? And the answer is absolutely yes. Okay? I can, in principle, take energy out of a system. Okay? That's doing negative work and causing negative energy on the system. But here's the challenge, and this is something to pay close attention to when you're solving these problems, is that in energy, there is no such thing in classical mechanics as an absolute value of energy. Okay? Energy only ever cares about differences from one place to the next. Only when we began to understand relativity did we say that there was some fundamental value of energy related to mass. In classical mechanics, it only cares about differences. Okay? So here's a weird problem. Let's say Amber, she put a ruler here and she raised a 1 kilogram rock about 1 meter. 1 meter off the floor. That's a skateboard. Awesome. Let's say that Amber here, I probably don't have a floor enough too. Anyway, 1 kilogram rock at 1 meter. What is the energy of a 1 kilogram rock raised to 1 meter? Can you guess? It's about a joule. Okay? 9.8 joules if you'd count G. I call G1 in this case. So if I do that, I raise this thing up, it gives me about 10 joules off the floor, and I say that the difference in height that I've gone is 1 meter. Okay? Now, what if you were standing there and your name was Bill, and you called 0 where the top of the rock was? When the rock was lifted, you said, no, that's my 0, and I see that this rock is going to fall to -1 meters. You see the difference? One person said the floor is 0 and I lifted it 1 meter. The other person says, no, I started it at 0 where it was in the air and it went negative distance, right? So here's a problem that we have to really be careful about is how can they both be right? Okay? Yeah?
Isn't it just a matter of what's the reference rate?
Absolutely, but we'll do it carefully. So it's the reference rate and you just have to keep track of the sum. And this comes back to whether you can have negative energies or not. Okay? So let me just dissect this problem. We'll answer this really carefully, but why can they both be right? In fact, they are. It depends on your reference frame and the coordinate system that you choose. This is going to be true in every problem that you solve. So let's look at an example to understand this. Let's imagine that rock now drops. I don't really have a good dropping object, but this little ball will do. I now start from some position and I drop it. As I go down, we studied this quite a bit. I can write down the y velocity as it goes down, so it's final velocity at some later time, as the initial velocity squared plus 2 times the acceleration times the distance that it travels. And we plug in g for this. This is just kinematics, week 2 of this course. I can plug in g, it becomes a minus sign, so I'm keeping track of the fact that this is falling in free fall. It's in the direction of the acceleration. And I just rearrange this thing. So all I'm going to do is take my kinematics equation that tells me about the final velocity, the initial velocity, the final height, and the initial height, and I'm just going to separate algebraically the terms that care about the final state down here and the terms that care about the initial state. Do you see that I've just moved some terms from one side to the other? Look at these 2 terms. You may see the clue already. This one, v squared, is a speed. This one is just the height above the ground. This is the state in the final position. The initial position has the same thing. It has the velocity squared, just speed squared, and it has the height in the initial position. If you look at what I've just written down, it tells us something funny, that this quantity, v squared plus 2gy, stays the same no matter where that object is traveling. Right? So when I drop this ball, whether it's in this position or a later position down or another position further down, in an ideal system, this quantity vy squared plus 2gy is constant in free fall. Right? This is all just from kinematics. And we would say, and remember this from momentum, that this quantity, v squared plus 2gy, is a conserved quantity. What does this look like? V squared looks like what? We just learned it today. If I add a 1/2 m in front of it, I call it kinetic energy. If I have a 1/2 m in front of this one, what does it look like? Potential energy. Okay? This is the gravitational potential energy and kinetic energy. When I think about free fall, the value of the sum of both of these things, kinetic plus potential, is a constant. And it just changes from potential to kinetic as it starts to move faster. Okay? So we would say that in a free-falling object like a rock that those 2 people were measuring, there's a conserved quantity called total mechanical energy. And we'll play with this in a second. So here's how we can think about it a little more carefully. So the total mechanical energy is basically the final kinetic energy plus the final potential energy. But we said that it's equal to the initial kinetic energy plus initial potential energy. And so if I think about what happens in free fall, is I go from the energy of position, gravitational potential, and as I fall, I'm transitioning into less gravitational potential energy, but more kinetic energy. Does that make sense? So if I drop this ball, right now it has 0 kinetic energy, it's all potential. Right before it hits the floor, it's going as fast as it can go. It's all kinetic and very little potential. Okay? I can transition. It's a constant amount, but I can switch between them. And the sum doesn't change in this system. So if you're doing a conservation of energy problem, you would say that the sum never ever changes. And the way we can write that is that the change in mechanical energy is equal to the change in kinetic plus the change in potential, and equals 0. Okay? Let's see what would happen. Let me do it again. I got nervous. What happened? Why did it hit me in the face? I know you all wanted it. Except for the few people that said, yeah, I didn't like this course. I still don't believe it. But if what I said wasn't true, this wouldn't have happened. What happened in this problem was that the kinetic energy at the top was 0. Right? It then converted into, it has potential energy that converts into kinetic energy at the bottom. It stops at the other side. What happens at the other side when it stops? The kinetic energy goes to 0, and then it's all potential. Then what does it do? It swings back, it turns back into kinetic, and then it swings up to my head, and stops just in time. Okay? What if I made a mistake, and I did it like this? Okay? That's called a broken jaw. Okay? I'm not going to do it. If I raise the potential energy higher, then it's going to have enough potential energy when it comes back to smash me in my face. Watch. Okay? There's a good way to do this demo, and I'm not going to do it today, is you actually do it with a big piece of glass right in front of your face. I'll do it next time. I couldn't find a good piece of glass like a brick. But do you see what the point of all this is? That there's some total energy that I put into the system. I do work. I introduce this energy into the system. It now has potential energy. It's going to stay in there. In a real system, what happens though? If this thing swings back and forth, is it going to go forever? Why not? I heard it. There's friction in the air that's doing what? It's doing work, negative work, on the system. The energy is slowly being reduced. Okay? So that in an ideal system where there's no friction, there's no drag, you have conservation of energy. In real systems, you have to account for the fact that, like in this case, the air is basically slowing it down. I had a question somewhere? Yeah.
So this equation of zero, where that is assuming no other outside forces.
Exactly. Yeah, exactly. So this is an isolated classical mechanical system. And we'll talk more about that. So now, here's what we'll say. Here's the way to think of this simply. In other words, this quantity, 1/2 mv squared plus mgy, is a constant for an object in free fall, or for an object moving along any frictionless surface. Okay? Like I can take this marble. This is another example. Here's a bunch of different tracks, and we'll answer some questions about these in a minute. If I start from this height relative to this one, it has very little, I'll start on this front one. It has very little kinetic energy, right? What's going to happen when I let go of the marble? It's just going to roll slowly. At the end, it's going to have much less potential energy and a lot more kinetic energy. Maybe the metal one. Watch, it's just going to go, whoop, shoots off. Okay? It doesn't matter that the path has a funny shape. The fact that I have a height, y, and that it converted into a speed, v at the bottom, is all I need to know for energy. Okay? I don't need to know the nature of that path that it took. As long as I know that there's nearly frictionless surface, there's no external forces doing work on the system. So we can write that down as, again, the sum of the mechanical energy before is equal to the sum of the mechanical energy after. This is a statement that energy is conserved. And this thing is called the total mechanical energy because we don't include thermal energy. We don't include anything quantum mechanical or anything relativistic. Okay? For an object under only the gravitational force, you then see that this is conserved. This is the law of conservation of mechanics. This is the most powerful tool that we have for solving problems. If I say I compress a spring by doing work on it, I've added energy to the system, what's the spring going to do? It's going to push back. It's going to want to become uncompressed. So I can actually study how fast that spring is going to move by how much I've squeezed it closed. Okay, so now finally coming back to Amber and Bill. Why does this work? It doesn't matter what reference frame I choose. It's because this equation doesn't matter, right? It just says all I need is the change in kinetic and the change in potential. So both agree that the rock is at rest at the beginning. So the kinetic energy for both is 0, right? The rock is sitting there still. I can write down 1/2 mv squared final, which is the speed right before it hits the floor. That's the final kinetic energy. And then I look at it, and it's the final potential energy minus the initial, but with a minus sign. It's the negative of the change in the potential energy. So according to Amber, the initial potential energy is mgy, so 9.8 joules, and the final is 0. So delta U for Amber is negative 9.8 joules. Right? It loses 9.8 joules of potential energy and converts it into 9.8 joules of kinetic energy. Now the same for Bill, right? His initial height he called 0. The final height is basically negative 1, which gives it negative 9.8 joules. And so for him, the change in potential energy is exactly the same, negative 9.8 joules. You see that all that matters in energy is the change in energy scale. I've changed by negative 9.8 joules. I can never say in a physics problem with energy that this rock has some fixed value of potential energy. It only matters when I compare it to some reference. And if you look at both, no matter which problem you solve, either calling the origin here or down on the floor, in both cases it loses 9.8 joules of potential energy, and so it gains kinetic energy to give it a speed of 4.4 meters per second. Okay? This is just a simple solution. I take 1/2 mv squared is equal to the negative delta U, I plug in some numbers and I get this. Okay? This is the most common type of problem you're going to solve over the next week and on the final exam. Are these problems where I ask, if given a total energy in the system, how much velocity or potential can I move around in the system to give me different movement? So here's a couple important notes. And this is really important for understanding how potential energy works, but also solving your problems. You can place the origin of your reference frame or your coordinate system and the 0 of potential energy anywhere you want and get the correct answer. Okay? It doesn't matter where I call the 0 of my height, as long as I'm keeping track of changes in height. But what I would say is, even though you can get it right, there are often choices that are better than others. Right? So when I solve a problem, I can conveniently choose where the 0 is to make my life easier algebraically. And those things only come up by practicing these problems. Okay? This is just like forces and torques. There's a whole bunch of tricks like this, where if I put the forces in just the right place, I don't have to write it down in the equation, especially in torque. Same idea. And for objects moving along frictionless paths, this is the most important part. If I say that it's a frictionless path, or there's no air drag, and an airplane is doing maneuvers without it, the potential energy gained as the object falls is transferred into kinetic energy independent of the path. Okay? So again, I could lift this ball up to some height. It says about a foot. I could lift it up to, say, 5 feet. It doesn't care about the path. It only cares about the gravitational potential energy stored in the ball right now. Right? If it was on a different road and it traveled the same height distance, it would change the same amount of speed. Okay? It doesn't matter what the path is. It only cares about the height and the speed. And we know that just from the equation. 1/2 mv squared is kinetic energy, or mgy is potential energy. So let's see if we can actually solve a problem. This one's kind of challenging. Only because it has a topic that we did last week, and I'm sure you've all forgotten. Or most of you. Take 2 minutes. So this is a really careful application of all the things we said, and one other piece, which is momentum. But you have 2 pendulums. I assume everybody knows what a pendulum is. We've been looking at one the whole lecture. This is a pendulum. Right? It's a mass swinging back and forth. Let's assume that you have 2. One is M1, one is M2. M1 is bigger, so this is any number bigger. And they're released from the same initial height. So I pull these 2 balls. I can be 2 different bowling balls of 2 different masses from the same height. Which will have the greater momentum at the bottom of the swing. Okay? Now what is momentum? Mass times velocity, or speed. Okay? So see if you can carefully write down, use our equation, the change in kinetic energy plus the change in potential energy has to be 0. And see if you can decide which one of these will have the greater momentum at the bottom of the swing. The heavier one, the more massive one, or the less massive one. So take about another minute or a minute and a half. Write this stuff down. I'll even go back really quickly. Here's what you need. It's basically this, right at the top of this slide. Mechanical energy is kinetic final plus potential final equals kinetic initial plus potential initial. That gives you everything you need to answer the question. You just have to do it really carefully. So take another 30 seconds. See if you can write this down. So far, so good, actually. Solve this energy problem first. Ask, what happens if I raise a pendulum by some height and it turns into kinetic energy? And then look at the momentum of the two. So take about 15 more seconds. Okay, 2 or 3 more seconds. There's a couple more responses left. Okay, you guys did awesome. So 80% of you said A, that the object M1 would have the greater momentum at the bottom. Okay? Some of you might have guessed. Many of you may have guessed. Let's do it carefully and make sure that we understand why. Okay? Here's how we solve these problems. We did this with momentum problems. We look at the before and the after. Okay? So there are 2 cases here. The before case is when I lift the pendulum up to their highest height. That's what I'm going to call the before case. Okay? The after case is when they're moving at their highest speed right through the bottom of their movement. That's my after case. Does that make sense? So I have the energies before, or initial, and then I have final, which is after. So let's look at M1. The potential energy initial for M1 is going to be M1 G times some height h. Okay, I'm just going to say they were lifted to the same height, h. They have a mass that's M1 or M2, and G is a constant. Now we'll do the same for M2. The initial for M2 is just M2 times GH. Which one has a larger potential energy to start? M1, because it's bigger. Okay? Now I'm going to look at the kinetic energy. So M1, I have kinetic energy, I'll call it final. So 1/2 M1 V1 squared. And I'll do the same thing for M2. Kinetic energy final, 1/2 M2 V2 squared. Okay? Do you see how we address the problem? I said that's the initial position, this is the final position, and now I'm just going to ask what changed in the system and how did the momentum change? One thing you see immediately, if I solve for the velocity of M1, what does it come out to? If I say that the kinetic energy is 1/2 mv squared, but that's equal to the initial potential, that gives me an equation that says, what happens to the mass in this equation? It cancels immediately. Okay? Mass in energy equations tends to cancel unless it's changing. Okay? What this tells me, if I solve for the velocity of the first object, is 2gh, or square root of 2gh. Okay? What is the speed of the other object come out to? The same exact value. Because in that case, mass cancels out as well. Okay? But the question that we asked was which will have the greater momentum at the bottom. If they both have the same speed, v, which one will have the larger momentum? The one with the larger mass, or m1. 80% of you got it right. I'm not sure if that's the reasoning you went through, or maybe you had a different way of thinking about it. That's exactly how it goes. When I ask about momentum, I'm taking mass times velocity. When I talk about energy, we saw that the mass actually canceled out in that case. That it was independent of those two systems. They both had the same speed. Now let's see if we can understand this a little bit more. Here's a really fun problem. Which of these sliding boards would be the best? Which would be the best one? In your opinion. Just give me an opinion before you answer here. Which one would be the most fun to slide in? I think it would be C. D would really suck. Right? The landing really stinks. Okay? These ones are kind of boring, but C looks really good. Okay? But now let's do physics. Imagine a small child sliding down these 4 different frictions. Has anyone ever done a really big sliding board? They don't have these here too often. But what do? You put something under your butt, right? Usually a rug, or even better, wax paper. Has anyone ever taken wax paper? Oh my God, it's terrifying. It's awesome. Why are you doing that? It's because you want a frictionless slide. So each has the same height. Rank in order the child's speed at the bottom of each of these slides. Okay? So which of these will give you the greatest speed? I think most of you are doing this pretty quickly. Take about 10 more seconds. A lot of you already have to answer it. So which, rank in order, their speed at the bottom of these slides? Wait a minute, pause for a second. What does our equation tell us? What is the initial potential energy for all 4 cases? mgh. What, therefore, is the final velocity for all 4 cases? It's going to be 1/2 mv squared. It's the same exact value. Type in the right answer, and then we'll come to why 30% of you had a different intuition. Which one? What's the answer? It's A. Conservation of energy tells us that all the speeds are the same. Wait, I'm not done. This is the interesting part. A lot of you said it was B.